Guys, we will be starting soon. We'll just wait a few minutes for those who want to join. To join. We will start by 6:05. So inform your peers, those who want to join, that they can join right now. Okay, all right. I think we should begin. Those who are left, they can join later on. but we should begin. So, good evening, everyone. Hope all of you are having a nice day. So, I'll just share my screen with all of you. All right. So, the regular two questions: Am I audible and is my screen visible? Am I audible and is my screen visible? Yes. Yes. Okay. All right. Good. Nice. Nice. Okay. So, let's start. So, today is the third session of Gemini Study Jams. So, first of all, let me explain a bit. So the session was supposed to conclude in 3 weeks, as we know. The syllabus was 3 weeks, but last week our activity was a bit longer, and that is why we were not able to cover all the points that we wanted to cover. And that is why a bit of last week is spilling over to this week, and we will this is, so as you can notice, the title is a supervised PFT using LoRa continued. So this is an extension of last week's class. That is because we were not able to cover every topic that we wanted to in that class, and we will cover that in this class so that we can have enough time for the last session. So we have extended the number of sessions by one. So uh, the next session will be the final one. This is a continuation of week two's session. All right, I hope I'm clear on that. And with that, we can begin. So, what were we not able to cover? So, going back, um, last week we actually read some code. We saw some code on how we can apply, parameter efficient fine tuning using LoRa on an open source model. So, if you would recall, we used Quen 1.53b instruct model, and we made it to use Shakespearean writing style in its answers. So that was what we did last week. We skimmed over a lot of the theory because we wanted to actually see some code. So what I have planned for today is just these four topics. So we will cover theory a bit because we were not able to do that. So what I realized is that nowadays, with all these generative tools and all these YouTube tutorials, I believe you should be able to code whatever you want. And if you have any doubts, you can always ask me on the Discord. So what I figured was that we can actually do some of the hard part. So what you will not understand by self-study, so some of the theory, we will look at what the hyperparameters, so what are hyperparameters and what they do, especially in case of LoRa. And we will today we'll go through the fine tuning of a closed model, which is Gemini, which is actually part of the labs you are assigned to do. And we will also talk about some general problems we need to consider when we are fine tuning. All right, so that is what we have planned today. Am I clear so far? Okay, all right. Okay, it says clear, Sarthak as well. Okay, all right. So that is the plan for today. So I guess we should start with the first slide. So how does LoRa actually work? We went into this a little bit during the last session, but it was all a bit confusing for all of you. So this time let's do it again, but just um, make it a bit more intuitive for all of you. So I'll share my OneNote screen here, which should be visible right about now. All right, so is my screen visible to all of you? Causal decoder only transformers. Okay, all right, so let's start with this. So first of all, we will, so to understand how LoRa works, what it actually does, we need a very small background on how large language models actually generate text. We went over this last time as well. So what I explained last time was that essentially what large language models are, they are just next word predictors. So for a sentence, they predict the next word in the sentence. So for example, if the sentence is something like this: today is a dash, They will predict the word that will come at the dash. And how will they predict that is what we're going to study today, to understand what LoRa actually does to fine tune. All right, so language models are predictors, they assign probabilities. All right, so to know what word will come next to generate sentences, what transfer architectures do, we follow a few steps. So the first step for any transformer will be to tokenize. So we went over this last time as well, that a language model does not understand English. So what we do is, first of all, we divide our sentence that we have. So from today is a, and we divide it into tokens. A token you can understand as a group of characters. So you can understand it that a token is a word. So, but not all right. Sorry, guys, I disconnected, but let's continue. There was a issue with the network, but let's continue right now. All right. So is my screen visible yet again? And am I audible? Okay. All right. Himana Sathak Chirag. All right. Yes. Okay. So let's get back to the explanation. So I was explaining to you how transformers work, and we will that is what we're looking at. So I said language models are giant next word predictors, and now we're looking into the process of how they actually predict the next word, right? So as I gave you this example that today is a, so first step was tokenization. So what is a token? A token is approximately a word, not exactly. So in real world scenarios, that rarely happens. A token is, as you can see over here, the token is today and space combined with it. And for the third token, it is space and a. So token is not just a word, it is, anything in the vocabulary. It can be exclamation marks, it can be question mark, full stops, all the symbols we have, the rupee symbol, the dollar symbol, all of that are tokens, right? So whatever input we have, we first of all convert it into tokens. So now the thing to note over here is that the size of the vector we will get after tokenizing will be one row, and number of columns will be however many tokens there are. So I think the first step is very easy. It should be clear what the first step is doing. It's tokenization, which is essentially dividing our words into tokens, because we are getting it ready for pre-processing. Hello, Manav. So first step, is it clear? Because I'll only proceed if we can get every step clear one by one. Okay, it's clear. Okay, all right. So this is the first step that any, so I should specify over here, although generally every transformer works like that, but we are tackling specifically decoder only transformers. What that means is beyond our scope, but if I get time, I'll explain to you. Okay, all right. So we have tokenized our input sentence. Now the second step is to embed those tokens. All right. So tokens, words have been divided, but they are still English letters. They are not numbers. And our language model, our transformer architecture can only process numbers. So now the task is to convert the word, which is a token, into numbers. So how do we do that? That is done using a vocabulary. So any language model, even modern ones. So if you're even talking about GPT-3, GPT-5, Gemini, Claude, all of them have a vocabulary. So what is a vocabulary? So as it's written here, so vocabulary is essentially a dictionary. So the first word in so a language model knows all of these words. So the first word is A, so it will go to the word starting from A all the way to words ending with Z. So Z, Z, Z is the last word. So the the expression when we are sleeping is Z. So that's why this is the last word. The first word is A, right? So a vocabulary is all the words a model can generate, right? So it is all the words a model knows, and every model has a specified vocabulary. So that is the words a model knows. So for example, GPT-3 has a vocabulary of around 50,000 words. So GPT-3 knows 50,000 words of the language, right? So this does not need to be in English only. So it can be tokens of Hindi letters, it can be tokens of Urdu letters, it can be token of Bengali letters, any language. These all fit into a model's vocabulary, the words a model knows. And each word in a model's vocabulary has a corresponding embedding. And the embedding is how that word is represented with numbers. That is the gist of this. And so what we do is we take our tokens. So we have today is an A, and we check what are the embeddings for that token in our vocabulary. So if I find that in my vocabulary today is represented by the number 437, I write 437. I find that is represented by the vector 158, then I write 158. Presented number 360, then I write 360. So that's what essentially embedding is we take our tokens, we check the model's vocabulary, that what words we have and how they are represented, and we convert our tokens into those words. So this is known as token embedding, which is part of the second step of our transformer architecture. Now, apart from token embeddings, we also have something called a position embedding. So a position embedding is, this will be better explained with an example. Sarthak says, is this based on Unicode encoding? Sarthak, this is actually embedding in itself is a machine learning procedure. So Unicode encoding will be very small for a machine learning model. What I mean by that is, this is just an example here. Every encoding has 3 dimensions, right? So 3 numbers. In real models, these are actually thousands of dimensions wide. So a number will be 1,000 vector dimensions. So this is actually not a scalar quantity. It is not meant to represent an encoding or a number. It is a vector. It is meant to represent an arrow in some n-dimensional space. So this is not like based on Unicode encoding. So this is based on vectors and how they are represented in space. Okay, so as I was talking about position embedding. So what is position embedding? So this I wanted to explain with an example. So the example is, let's assume there are two sentences. The cat ate the rat, and the second sentence is the rat ate the cat. Now what you will observe over here is that both these sentences have the same words, and those words are the and cat, and ate the rat. So these are six um, these are six words we have in both sentences. Their ordering is different, and a different ordering of words means a different meaning. So if we just used token embedding, we would get the same embedding for both these sentences, even though the order of the words is different. So what we do is we use a position embedding. A position embedding tells us that if a word has position I in the sentence, how does it affect our ability to comprehend it? That is what a position embedding is. So what we do is we take the token embedding, which is the vocabulary the model has, how a word is represented by the model. We add to it the weight of the position. So the first position has this position embedding. So if any word is on the is the first word of a sentence, if any token is the first token of a stream, this position embedding will be added to it, and we add these both and we get our input to the next layer, which is denoted by X. All right, so is this embedding step clear to all of you, what we're doing over here? The second step. Okay, it's yes, so it's clear to Hokesh, the embedding step. What we're doing, we're taking the input tokens. Sarthak says, please repeat the weightage part. So Sarthak, what I said was for position embeddings specifically, right? For position embeddings, if you have two sentences which have the same words, the cat ate the rat ate the cat, the order of the words is different. But if we just take token embeddings, how we embed both sentences will be similar. But the position of the words also matters in the sentence. So what a position embedding does is that it essentially gives a weight to each position in the sentence. So every token, if it appears at first position, it will have some weight. So that's how this affects our sentence. So the cat at the third position and the rat at the third position mean two different things. That's what I mean by the position embedding adding some sort of weight to our input vector. Okay. And I hope the second step is clear to all of these. So the first was tokenization. The second step was embedding. All right, so let's move on to the third part. Now, this is the important part, and this is where Laura will also come in. Right. So the third part is attention. So this is the new revolution that transformers bring to the table, right? So this was introduced in the 2017 paper, Attention is All You Need by Google. And so what happens is that now we have our input ready to process. Now we need to understand what those words mean, how those words that the user has given us correlate to each other, and then we can predict what the next word will be. So we get our input X, and so a transformer architecture, decoder only, has multiple heads. So what are heads? So heads essentially tell us what word should focus on what other word. So for example, let's say I have a sentence, I ate the apple, right? So the word ate should be looking at apple because those two are relevant in a context of what action I took, right? And the word ate should also give attention to the word I to understand what the next word should be in the sentence, which should be a full stop because this is a complete sentence. So each head is a different way of looking at our sentence. So the first way, as I explained to you, right? So there are lots of heads, thousands of heads, and a group of heads gives us one way to look at our sentence and gives us one way to know what word should attend to what word, right? So as I gave the example, I ate an apple. The word ate should pay attention to the word apple because that's describing what I ate. Now, if we look at it from the perspective of another head, that head might say that the word ate should pay attention to the word an because ate starts with a and therefore we use an in place of a. So it grammatically incorrect would be I ate a apple. Grammatically correct would be I ate an apple. So the first head is telling me as an action what I should pay attention to. Ate should pay attention to the word apple. And the second head is telling me from a grammatical point of view what I should be paying attention to. There are lots and lots of heads in a transformer architecture, and a group of heads tells us something different about the sentence. Each group of heads tells us something different, and all those add up as knowledge that we can use to predict the next word. So what actually happens here is, so as you can see, so we have multiple heads. Here I've represented three. It is denoted by this letter H, H1, H2, H3. And so so for every single head that we have three vectors. These are known as learned projection matrices. So what these are? So these are essentially what we learn in pre-training. So these are actually what tell us the meanings of the words. If you want to think about it intuitively, these are learned in pre-training. These are what we are not concerned with. So the models we use come pre-trained. We are just fine-tuning on them. So these are as given as input because these come with pre-training. These learned projection matrices allow us to get some meaning out of the sentence from our head's point of view. So each head has these three matrices, WQ, WK, and WV. And with using these three matrices, for each head, we calculate three of our own matrices, which are Q, K, and V. And so Q here stands for query, K stands for keys, and V stands for value. So now these three answer three very important questions. The matrix query tells us in numerical form, what am I looking for? So what it's telling me is that what word. So in the sentence, I ate an apple. The value of query matrix at the token of 8 will tell me what am I looking for. What kind of word am I looking for? If it is apple, it will be biased towards apple. If it is I, it will be biased towards I. If you are looking at it from a grammatical point of view, grammatical head, then it will point towards an. So the query vector will tell us what a word is looking for, what a word wants. The key vector will tell what the word offers. So that means, so what I can give to the sentence, and Q tells us what I'm looking for in the sentence, and V tells us if selected what data will I pass to the next layer. So this is very technical stuff, but on a higher level we can think about it like this, that for each head, so there are multiple heads, each head represents a different way of looking at a sentence. Each head has its own learned projection matrices, which we learned during pre-training. So these are given to us already. What we do is, using these matrices, we calculate three matrices of our own which matter to us, which are Q, K, and V. Query, key, and value, which tell us what I am looking for. So I means the word here. So for each word, from the perspective of one head, Q will tell us what the word is looking for. Key will tell us what the word offers to the other words in the sentence. And V will tell us if that word is selected for the prediction for the next layer, then what will it pass on? I know this can be a bit confusing, but as a general overview, you can assume that. Right. So is this part clear so far? What a head means and what we mean by Q, K, and V, because this will come out later. So I'm just confirming if all of you understand what I mean here. If you want me to repeat any part, just say it in the chat and I'll repeat that part. Otherwise, we should move on. Okay, not very clear. Okay, says a little bit understood. Okay, Alex, I'll try and explain this to you again. So we have our input, right, which is the vector x, which is, we tokenized our sentence, we turned it into embeddings, and now we have those embeddings ready to use. Now, how do we understand what word we want to predict? What word will be the next word? So for that, we have the attention layer. Now, what the attention layer is it tells us what word should focus on which other word in the sentence to know what the next word will be. So essentially what I mean is that it helps us understand the context of the sentence better. So for example, if I say something like, India is a very ancient country. India, it is a subcontinent, like a peninsula, all that. So the context of that sentence is historical, right? But when I talk about India in other context, so for instance, if I talk about India in terms of its culture and heritage, so India has a diverse culture and heritage. The context becomes different. Or if I talk about India, let's say India is the name of a person, that is also different context. So what this attention layer allows us to understand is that in what the context means. So in the given input, what should each word be focused on? So what word gives the current word meaning? And so each group of head will give us a new way to look at the sentence. So for example, one group of head may allow us to know check its grammatical correctness. So like the example, I ate an apple. So it will tell that ate should focus on the word an, because that will be the correct grammatical usage. And if we look at another head might tell us that ate, I ate an apple. The word ate should focus on the word apple, because that's what I'm eating, right? So each head gives us a new way to look at um, the sentence and provides us with more context. And so using all the heads with further processing later down in the model, we can actually predict what the next word in our model should be, right? So how this is actually done in mathematical terms is that each head has three matrices: wq, wk, and wv. Let's treat them as black boxes for now, that they are already given for each head. So what we calculate using these three is q, k, and v. So we multiply our input x by wq, we multiply our input x by wk, and we multiply our input x by wv. And this multiplication gives me my own matrices q, k, and v. And Q stands for query, K stands for key, V stands for value. Now, what query matrix tells us is that for X, Sarthak, X is the input that we got in the last after embedding, right? X is the input that we got after embedding, and WQ, WK, WV are what we already have due to pre-training process, right? So we calculate our three matrices Q, K, and V for each head. So if there are 1,000 heads, I will have 1,000 Q matrices, 1,000 K matrices, 1,000 V matrices, and these matrices will answer from the perspective of a particular head what the ith word in this matrix should look for. So for example, if the token 8 has the index 3, so what so the numerical value in query matrix at index 3 will tell us what other word should 8 be focusing on, should pay attention to as its context. Key matrix will tell us what the word 8 can offer as context to the other words in the surrounding. And we will tell us that if the word 8 is used to generate the next word, what value should it pass to the next layer. So this is a bit technical. You don't need to pay much mind to it, but just an high level understanding. So if you understand this so far, if you don't, we can go again. What we're doing in the attention layer, we have multiple heads. Each head will give us a new way to look at our input, and that will inform our choice for selecting the next word, is essentially what's going on. And how we understand the context is using these three matrices: query, key, and value, which tell us what each word should be paying attention to, what each word offers to the other words in the sentence, and what value it will be passing on if it is used to generate the next word in the sentence. Is this clear? Okay, says yes. Other people is it clear? Okay, says yes. What is the benefit of using attention layer? Sarthak, attention layer is the whole mechanism behind language models. So before attention layers, we had other techniques. We used RNNs and LSTMs for generating models, but the models that came out of using them were not very strong. So when this concept of attention was introduced and they were used in transformers, our models became very, very powerful. So there are multiple problems associated with models we have previously used, like RNNs and STMs. But one big advantage of using transformer layers is that they stack on top of each other. And so far, what we have seen is that to increase the efficiency of a model, to get better results from our language model, we just need to add more attention layers on top of our architecture, and we also need to train it on lots and lots of data. Um, all right. So other LLMs also use attention layer other than Gemini. So Sarthak, this mechanism attention is a general concept. So most modern LLMs use this concept as a foundation. So every major LLM uses attention as a mechanism. Their architecture may be different. So attention layer may come before or after some other layer, but mostly all modern models use attention because it is the breakthrough invention in language modeling. And coming back to Hokesh's question, is this what is happening behind transformer, right? Yeah, Hokesh, this is what happens in the transformer architecture. So transformer architecture is the architecture used by most major language models. So we will get to what fine tuning is doing here, but you need to understand a little bit of this background so we can actually get to that. All right, so since we understand this, okay, all right. So don't pay attention to this a lot. So what essentially happens is we calculate the attention using QKV. Let's not pay much attention to it. So we essentially apply a softmax activation over Q into K transform gives us the attention matrix, which we then scale down by a factor of root D of H. Then we apply softmax over it, and what you need to know is that this gives us attention, this formula, right? So we use QKV to calculate this attention, right? So this line summarizes it from head H POV. What tokens should each token pay attention to is what we are. So what you need to know is that after the end of this process, we will get a matrix that will tell us what each token should pay attention to, and that will be used in further layers to inform the decision for the next token, what we should be generating. All right. So this is as far as we'll go into the transformer architecture, because this is essentially where fine tuning using LoRa works. So after then there are a few more layers, but this is for where LoRa actually affects the model. And this is where LoRa shows why it is a better technique than full fine tuning. So now let's look at this. So, so in fine tuning, what we do is in the attention layer, so all right. So as I said, we had three learned projection matrices: WQ, WK, and WV. So what fine tuning does is, let's go back to the basics. So in the first session, as I said, fine tuning is to reveal a particular style of generation. So to talk like Shakespeare, or generate images that follow anime style more consistently, or to generate audio that matches a particular voice, a particular cadence, right? So that is only done because we know these three matrices. Now to change the way we generate to adapt a particular style, in fine tuning we change these three matrices. So these are our targets. So this is what we will change if we want to change the style of generation of our model. So in fine tuning, what we do is that we replace these with this plus something, and this something is the change, right? So initially we started with this in the pre-trained model. What we turned it to, we turned it to WQ plus delta WQ, where delta WK is the change. So the takeaway here is we need to know how we should affect WQ in order to get the results we want, how we should affect WK in order to get the results we want, how we should calculate WV in order to get the results what we want. So what I want you to understand over here is, so in the fine tuning process, to get the particular style that we want, as we already discussed, we are not inventing anything new. It is already there in the transformer. We want to make it happen more often. So we have three matrices which had in the original pre-trained model: WQ, WK, and WV. These three will affect how we generate our tokens, right? So our aim with fine tuning is to change these three in a way that supports the tokens we want, and to change them we add something to them, and that something is what we need to calculate, which is the goal of all fine tuning processes, made by full fine tuning or parameter efficient fine tuning. For every kind of fine tuning, we need to know how we will change our projection matrices so that they more often support the words we want, or the type of image we want to generate, or the type of audio we want from a generative model. Is this much clear? Because this is the foundation. So what I said was, the gist was that we have these. So how we generate depends on our learned projection matrices WQ, WK, and WV, which we saw earlier in the attention layer, right? So the goal of any fine-tuning process would be to change these matrices by adding something to them, so that these matrices more consistently support the styles we want. So it supports a Shakespearean style of writing. It supports a cyberpunk theme of generating images, or it supports a particular audio cadence, right? So this is what I mean by this. Is this clear to all of you? That's why we cannot add any new data when tuning. Yes, Hukesh, that's the reason why we cannot add any new data, because we are not actually adding anything new. We already have these WK, WQ, and WV matrices. What we can only do is that we can change them in a way that supports the style that we are going for. We are actually not adding anything new to the transformer architecture. For that, we will need to retrain. So yeah, that's correct. That's why we are not adding anything new. Okay, all right. It's clear to you. Okay, if anyone has any doubt, they can ask right now. Okay, I think nobody has any doubt. So let's. Okay, all right. So now, so we already established that the goal of fine tuning is to change these learned projection matrices so that they support our style more consistently. Now, in full fine tuning, so FFT is full fine tuning. This WQ, WK, and WV are calculated using these three initial matrices. So that means the full matrix is updated, right? So the size of the update is the size of the initial vector. So for example, as I gave the example in last session, if we have 175 billion parameters in full fine tuning, we will need to calculate these three matrices by going through all those 175 billion parameters. That is why the computation in full fine tuning is very large, because in full fine tuning we calculate these three matrices using the initial projection matrices, and the initial projection matrices have dimensions equal to the parameters of the model. And that is why in full fine tuning, when we calculate these three, it is a highly expensive, computationally expensive procedure, because the full matrix is updated essentially. But this is where LoRa comes in parameter efficient fine tuning. In parameter efficient fine tuning, so what researchers observed was that after we do some changes to our matrix, after we perform some changes to our learned projection matrices, they saw that a lot of the changes that were done were zero. So that means that a lot of what we are updating, a sort of 175 billion parameters, a lot of updates do not actually change anything. So that means, so for example, we took the example of Shakespeare. So the vocabulary of Shakespeare is, maybe 1,000 words, specific words, though, die, all those words, right? But what about the other millions and billions of words in the vocabulary of the model that are not related to Shakespeare? So common words, or common English words, or mathematical terms, scientific terms, because we know that the language model is a very big thing. It consists of millions and billions of parameters. So, and Shakespeare will be a very, very, very small part of that. So what they observed is that when we actually change these matrices, a lot a lot of the parameters are actually unchanged. That is, they do not experience any change. So what researchers observed was that if after fine tuning a lot of the parameters remain unchanged, why should we um, waste compute on parameters that are not essential to the fine tuning process? why don't we only update parameters that actually affect us, that actually improve the model's performance? So that was what the gist was. So what they saw was that the change in after fine tuning, after full fine tuning, they saw that a lot of parameters did not change because the language is very large, and whatever fine tuning purpose we are using it for, maybe only a very very small fraction of the entire language. So for the Shakespeare example, maybe 1,000 words out of the millions of words in vocabulary. So what we observed is that the other millions of words do not change at all. Only the words related to the Shakespearean style of writing are changing. So the conclusion was, why don't we only change the parameters that actually affect our model instead of updating the entire model? So that was the gist behind LoRa and parameter efficient fine tuning. And so they devised a clever way. So in more technical terms, the rank of the change matrix, the intrinsic rank of change matrix is very low. So what that means, that's just a bit of mathematics to say what I just said. So rank is just the number of independent rows, but you will study that, I think, in your coursework as well. In discrete mathematics subjects, you will deal with matrix ranks. But what they mean to say is that the not all parameters affect equally, right? So the intrinsic rank of the change matrix is very low. So what we can do is that we can actually calculate the change in that using two matrices B and A, which have dimensions which are much much smaller than the dimension D, which will be the dimension the dimension in full fine tuning, right? Which is equal to the model size, so 175 billion parameters. So what if instead of using the original projection matrices to know how to change them, we use two matrices B and A such that their dimensions are very small as compared to the dimensions of the model, and use those to calculate how our learned projection matrices will change. So we will take a breather over here. I'll ask all of you if you understood what I was trying to explain here, and you can ask if anything if you did not understand what the gist of this was. So, all right, was I clear here on this point? Why full fine tuning is not good and why PFT is better. Thank you, Himana, for doing a great job. Thank you very much. To the others, if it's not clear, I can explain again. So, Sarthak says it's clear. Okay. Okay, it seems like it's clear to all of you. If you have any doubts, you can ask away. I can re-explain this part, but if it's clear, I think we should continue. All right, so that's what we learned. So how PFT does. And so what actually are these A and B matrices that I'm saying that we will use to update the model? So as it's written here, A tells us which directions in input should we pay attention to, and B tells us how to inject that adjustment into the output space. So this is just mathematical jargon. So I'll just, for completeness sake, I'll go over what I mean by that. So what A does is that it takes the entire change in all 175 billion parameters, and it compresses it into a smaller space of size R, right? Where R is much smaller than the 175 billion, right? And what B does is that B takes that smaller compressed space and maps it again onto the bigger space. So in matrix terms, doing multiplying two matrices of dimension D cross R and R cross D, where R is much smaller than D, is more efficient than multiplying matrices that are of size D cross D. That is the mathematical gist. But in so, regular terms, A is just taking all that information of change, it is compressing it into a smaller space, smaller vector space R, and B is taking that smaller vector space and it is again mapping it to the entire bigger space, right? So, and the important part over here is that the original weights are frozen. right? So W is frozen, WK, WQ, WV that we were talking about are frozen. What I mean by frozen is that the fine tuning process does not change their values, right? So what this means is that the original remains frozen. We calculate delta W and then we apply it. So that is why we say that LoRa does not change the architecture of our transformer, because it's a mostly non-invasive process. We don't actually change any architecture of the model. We just inject quietly the matrix delta W by calculating B dot A, and we do it like that, right? So these are few points. So as I said, delta W is usually very low rank or close to low rank in technical space. The delta W intrinsic rank of delta W is low rank. So the number of independent rows in delta W is very less. So that just means that not a lot of weights in delta W are actually contributing. So this means that the changes needed to adapt a pre-trained model to a new task often lie in a small subspace. Most of the full D cross D matrix does not need large changes, only a few directions matter. So that is how I gave you an overview of how actually this works. It is nice to know this because if you are going for if you are going for a role in machine learning, they expect you to know all of this, and even on a deeper level you need to know all the mathematics behind this if you want to go for a machine learning role. But in a general use case you will usually not encounter the depth too much depth. We will encounter some sort of depth, but not a whole lot. All right, so let's move on to back to the slides because this was all. But before that, let me just ask if anyone has anything from this whole OneNote page to doubt or re-explain. You can ask right now, or we'll get back to the slides. Um, okay. If anyone has to ask anything, you can ask right now. Otherwise, we should head back. Okay, all right. I'll switch my tabs. If you need to ask anything, you can just interrupt me. So let me just stop sharing and I'll reshare my tab this time. Okay, all right. So we covered this slide, and uh, all right. So my screen should be visible right about now. And now let's move on to the next slide. So we talked about how does LoRa work, and now let's talk about hyperparameters. So what are hyperparameters? Um, like we say metadata is data about data, right? So in the same way hyperparameters are parameters that define the parameters of a model. So what that means is that, so in any machine learning model you are training something. Sorry guys, so actually I'm in hostel right now because We have some classes going on, but so the net here right now is a bit finicky. So I'm sorry for the interruptions, but I think we should continue. Sarthak says no audio. Am I not audible? Am I not audible? If I'm not audible, just refresh once. Naman says it's fine. Okay, all right. So let me share my screen and we should continue. So we are on a bit of a tight schedule here. I don't want to waste a lot of time. Um, all right. So I think before we get no, I think these hyperparameters are more important first. So all right. So we were talking about hyperparameters. Okay, Sarthak says now found now fine. Right. My screen should also be visible. Is my screen visible really quickly before we start? Yes, yes. Okay, all right, all right. Let's start. So, what are hyperparameters? Hyperparameters are parameters that decide how our parameters will be calculated. So, for any machine learning model, what we are actually trying to learn is the value of the parameters. So, in the case of the transformer architecture, we were seeing there. I said that uh, Q, WQ, WV, and WK were already given to me. How were they already given to me? Because they were calculated. So those are parameters because they were calculated during pre-training. Now hyperparameters define how those parameters will be calculated, right? Um, that's what you need to know for now. So LoRa during the fine tuning process during PEFT has a few hyperparameters of its own, which decide how the fine tuning process takes place. So the first one over here, as you can see, is the rank R. R is the rank of the low rank update. So as I said, R was the dimension of the vector A and B that we were using to update the weights of our language model. So as it's written here, if we take a small r, that means there are fewer parameters, right? Which means that we are not affecting a lot of parameters. So that means that we are computing less. So of course it's cheaper, but what that also means is that we are sacrificing the amount of parameters we affect. That means it's less expressive and less in the manner we want it to work. And a larger R means the fine tuning process will be more expressive because we are affecting a higher space of parameters, and it will be more computationally expensive. And the higher Gurdeep has his hand up, so if you want to say anything you can say. But larger R means that it will be closer to full fine tuning, the larger your R will be. So the more parameters you will be affecting, it will be more computationally expensive. So usually we take R like 4, 8, or 16, right? So for lower tier CPUs and GPUs, you will usually take 4, but for higher tier, if you want better results, you can take 16, right? So that's what R tells us. And we also went through this. So if you had revised the code, you will see that every time we do this, we define this hyperparameter in every. So in the last class as well, there were these hyperparameters R and alpha and all of that, right? So you have to define these during the coding process as well. So what you want to take your R. Usually it is recommended to play around with hyperparameters, take R as 4, alpha as something, and then check how your results are, then change them to get to the optimal hyperparameters that will give you the best results. All right. Another hyperparameter is alpha, which is the scaling factor. So alpha will tell us that all the changes, how heavily they should be applied. So it controls the magnitude of the adjustment. So fine tuning will tell our model to use this style, but alpha will tell us how heavily you should use that style, right? So it controls the magnitude of the LoRa adjustment. Similarly, higher alpha means that the changes we are doing have more influence because they are higher weighted, and the lower alpha will mean that the tweaks are subtle, right? As always, as I previously said, that the best way to determine what will be fit for my use case, what R should I use, what alpha should I use, would be experimenting around with R and alpha. See what value suits you, right? What value suits your case best, right? Another hyperparameter is the target modules, which are weight matrices. So this means that what parts of the model should LoRa specifically affect. So we talked about Q, K, and V, right? But there are others as well. So but usually our cases and that we can just use Q and V projections and that will be enough. But sometimes it's not, and we can actually affect other projections as well. So these are the hyperparameters of that we use in LoRa. And before that, let me just show you something as well to drive the point home. Right, let me just stop this sharing and let me just share something else really quickly. um, all right, so this is the code we were looking at last time, right? And so, wait, is my screen visible? I think it is. Okay, all right. I think my screen should be visible now, right here. Okay, now here, if you'll see that in the previous class, we imported our mod, we configured our LoRa, we actually set R. We used R as 16 and we used alpha as 32, right? And we also defined the target module. So now Q proj means. Q proj means the Q projection that we were talking about. So if I set the target module, so it will affect the Q vector. If I set V, it will also affect the V vector, right? So anytime you want to do fine tuning, you need to define these hyperparameters before that, right? R, alpha, and the target modules. And the task type is not that essential, but all right. Right, so this is these are hyperparameters. So if you have any doubt in that, you can ask away right now. So we have R, alpha, and the projections that we want to affect. R tells us how what space, so how large of a space should our fine tuning process affect. Higher R means that you are moving closer to full fine tuning. Lower R means that you are not affecting as many parameters. Alpha tells us how heavily should we affect, and target modules tells these target modules tell us what should we affect. Right? Is this clear? Is this clear to all of you? If you have any doubt, you can ask for hyperparameters. Okay, all right. I think we should move on now. Okay, it says it's clear. All right. So I think we should move on to the next slides. Okay, let me stop this. Let me share again. Okay, all right. So we talked about the hyperparameters. Now let's look at some code. So so now we will look at the lab we had in the first week, which was fine tuning Gemini. So that's what we will look at right now. So let me actually share that one. Just to give you an idea of what that is, I'll also show you that. Right, let me get back. So this was the lab we were assigned, supervised fine tuning with Gemini for image captioning. And this is what we will walk through. So let me just start the lab and let me just open it in a private window. It's usually recommended that whenever you are doing cloud labs, open them in a private window instead of your account window. Let me share that with you. All right. All right. Okay. Is so I think my Google Cloud Console screen should be visible here. Right. So let's talk about this. So our aim with this lab was to perform supervised fine tuning on Gemini for a task. Now, when I work through this lab, it is a bit outdated, but a lot of parts we can learn something from. So that's why we are going through it. So this is the Google Cloud dashboard. I'm not the cloud expert here, so I don't know much about it. But what I do know is that Vertex AI is the cloud ML library by Google. So as I talked about in the first session, uh, two types: closed source, open source. What we have been doing so far on Google Colab was we were taking open source models, so those models whose code and weights were available publicly, and tuning them for our own use. Now, Gemini is a closed source model. We don't have its source code or weights. So that's why to access these open sourced models, they are usually behind a paywall. And that paywall in case of Google and Gemini is this Google Cloud platform, from where we can access these models using their component Vertex AI. Now, Vertex AI is what Google uses as their cloud handler, I should say, for anything related to machine learning. If you have on Google Cloud, you will use Vertex AI. There are a lot of nice features to it. Auto ML, so it will do a lot of machine learning tasks for you. But right now we are interested in how to do supervised fine tuning with this. All right. So what I'll do, I'll go to Vertex AI. So if you did not follow what I did, um, you can actually just go to this navigation menu. These three lines on the top left. Click on them, and we'll go to Vertex AI. And what we are concerned with is the workbench, right? So you click on the workbench. Now, what this will show us, this will lead us to this screen where once this loads, we can see that we actually have a workbench already present for us. So this is what the lab created for us, and its name is Vertex AI Jupyter Lab. So this is the instance name we will be working with. All right, so now this is the cloud part of all of this. So to actually fine tune these closed source models, so in this case Gemini, you need to have cloud credits, right, which are usually worth real life money. But uh, for this program, Google has provided us all with free credits that we are using to perform this lab. For other closed source models like OpenAI as well, for OpenAI models, you will need some credits for to use them, to fine tune them. All right, so I'll click on Open Jupyter Lab. So this will lead me to the Python notebook where the code is written, and we can start reviewing that code and what it actually does here in the first lab. All right, it's loading a bit slow. In the meantime, I'll just look at chat. If anyone wants to say something or ask anything, you can ask. Okay, all right. So we are here. So we will be greeted by this screen. So this is just a Jupyter Notebook environment in the cloud, right? So you can actually just download Jupyter Notebook on your system and use it that way. But this is specifically with this is integrated with Google Cloud to have all of the services that Cloud provides us with to be used here. All right. So what we are concerned with is, so as you can see, there are certain options here. So we can create notebooks for with any of these kernels, but for us, there already has been a notebook created here. So as you can see, it's SFT Gemini on image classification captioning. So I'll open this notebook by double clicking on it, and this opens my notebook. So this is a notebook. So this is similar to Google Colab. So those of you who have not worked with notebooks, we have cells, we have text. So we run cells which have code in them, and you can actually just nicely write all this code as well. All right, so the first cell is just copyright stuff. To run a cell, you pressed Shift Enter, right? It will run the cell and move you to the next cell, right? So the first cell is copyright and license, right? All of that, what license it is, and all right. So now we get to our task. So our task is supervised fine tuning with Gemini Flash. So the model name is Gemini Flash that we're using for, and the task we're using it for is image captioning. So what is image captioning? Given an image, write a caption for it, write a suitable caption for it. Of course, regular Gemini Flash can do it, but we want it to be more descriptive with image captioning. That's why we are performing fine tuning on this task. right? It was written by Deepak Munath, right? All right. So you can read all this. So what this says is Gemini is a family of Gen AI models developed by Google DeepMind, right? So all of that, so it just tells you what Gemini is. We all know what Gemini is. It is a foundational model developed by Google DeepMind specifically, right? So our objective here is use Vertex AI to fine tune Gemini Flash. Now Vertex AI, as I said, is the cloud platform to perform anything related to machine learning on Google Cloud, right? So let's get to some of the code, right? So now first, so this is the first piece of code we are encountering here. This is just to install necessary libraries. So we have pip install. The upgrade flag tells us, so whenever I minus minus write minus minus, it tells that it is a flag. Upgrade flag tells me if I already have a library installed but there is a newer version available, upgrade the library. User tells me that I should only install the libraries on this account, so whatever account this notebook, whatever cloud account this notebook is associated to. The quiet flag tells me that do not debug do not write a lot of text, just do it quietly, right? And these are the libraries I will be installing: Gen AI, Cloud AI Platform, JSON Lines, and Rogue Score. So what is Google Gen AI? Google Gen AI is the software development kit for Python developed by Google to use language models produced by Google. So Google Gen AI is what you will use to interact with Gemini, Gemini Flash. What is Google Cloud AI Platform? This is to access. So this is the Python SDK to access the cloud's AI capabilities, Google Cloud's AI capabilities. JSON lines is the type of, so it is a library that gets input in the form of JSON lines. So what are JSON lines? JSON lines is nothing but a file where there are multiple lines and each line is a JSON object. Why specifically we are using this? Because this is the type of input that the fine tuning function takes. This is the type of data it will accept. What is rogue score? Rogue score is a metric to evaluate how well we perform on a generation task. We will get to this later on. All right. So now I'll go through some of these codes. So this is just, after you install the libraries, they tell you that you need to restart your kernel. So I'll just press shift enter here and you'll see that my kernel will die. So first of all, they tell me that kernel is restarting. I'll click on OK and it will soon become idle. All right, it's back up. So we restarted. Now we set up some cloud credentials. So the project ID is already given to us, right? So this just binds whatever we do to our Google Cloud. So I'm just setting a universal variable project ID here. That is the ID of my Google Cloud project, right? And I also set the region because uh, any compute, so region just tells us where physically the compute is done, because the cloud essentially means that the compute is being offloaded to somewhere else. So the region tells us that what region our the cloud instance is based in. So in this instance, the our cloud capabilities are being done from US East 1, right? These are again some universal variables. We are not here for the cloud part, we are here for the machine learning part. But before that, really quickly, if anyone has to ask anything, because I think this should be clear. This is, but if you have to ask anything from all of this so far, that then I can entertain it out. So ask away if you want to ask anything. So it's clear to Hokesh. All right. Anyone else, if you want to ask anything about this so far, you can ask. Okay, I think there are no doubts, so we can continue. All right. So now these are the libraries we will be using. Going through each library, let's talk about what they will do. IO library is just to read bytes. So everything is at the end of the day bytes. But if you have a stream of bytes, so continuous bytes incoming, and if you want to read them as so to read a, so let's say an image is represented as a stream of bytes. To read that, you will use the library IO. Time is for time related functions. You can ask the program to wait a few seconds using a function time.sleep. You can ask what the current exact time is. You can calculate all time related functions. Now PIL is a library that deals with images. So this is the pillow library, PIL, and this is used to modify, save, create images. So that's for animation. We'll import GenAI. So now this GenAI library, as I said, is the client that will allow us to interact with language models by Google, such as Gemini, all of those models, right? Right. And so yet again, we have AI platform, and types is just annotations for that, hints what kind of data types we are using, especially for GenA tasks. So we'll get to this later as well if it's used somewhere later on. So JSON lines, as I previously explained, the fine tuning job will take input in the form of JSON lines. So that's why we are using JSON lines library, because this makes it convenient to turn our data into a JSON lines format. And pandas is your, it's a very well known library, data manipulation from Rogue Score. Rogue Score is an evaluation metric for how well we did. Rogue Score tells us for a generative task how well the model performed. How exactly we'll get to later, right? TQDM is just for, TQDM adds progress bars to any. So let's say you have a loop for I in range 10. If you do for I in range for I in TQDM range 10, so it will just in the output it will add a progress bar that will go from 0 to 10. That's all TQDM does, right? Okay, all right. So we got all our libraries. Now we initialize our AI platform, right? So we create a Vertex AI and the GenAI SDK using the AI platform library that we imported. That initialize init stands for initialize with this project ID which we defined earlier, and the region that we defined earlier, right? And then we also get our client that will help us to interact with the language models by Google. So we initialized our client here as well, GenAI.client. Vertex AI2, that means that we want to use Vertex AI, set our project ID and location. Since this is a cloud environment, we usually will always set these two things, location and project. Right. Now the task is to prepare the data set. So as I said, the task here was to fine tune a model to caption images. So generate an appropriate caption for an image. So if I'm holding a phone in the image, one caption can be that the person is holding a phone. Another caption can be more detailed, that there is a, hand in the image with light coming in from the right side of the image with a green colored phone in his hand, right? That can also be a caption. So what we want is detailed captions. That's why we are doing this, right? So there are a few notes. So we will take images and text as input. So each input will be an image and then a comment accompanying text which will say generate a caption for this image or something along those lines, right? And we only want text as output. All right, so we are taking maximum of 30 images per tuning sample and maximum file size is 20 MB. All right, and our file should be in JPEG or PNG format. But we don't need to worry about that because all of the files that we will be using, files that have already been provided in project by default in the lab, right? So now they're explaining what a JSON Alpine is. So this is a JSON object. So if you don't know, JSON object is just these brackets, and inside that we have key value pairs. So this is the key and this is the value of the key, right? And so we have contents and this is a list, and inside the list we have another JSON object, right, which has a role. So the role tells us that we want to generate something new. Parts is interleaved image and text could be. So this is just what we are sending to our model. So first of all, there will be some file, the file type, where the file is located, right? And this is one part of the prompt we are sending, and the other part of the prompt will be the accompanying text, what is in this image, right? So this is just how you send queries to Gemini using the Cloud SDK, right? That's what we are what's happening here. All right. Now they're telling us that the data that we're using is actually available on a public cloud bucket, which has this ID. So if you want, you can check it out, right? So now they're giving us a sample of what the data set is like. So there's a prefix and a suffix, right? The suffix is the expected response, right? And there is no prefix because there is no additional text. The text will remain the same for everyone. Generate a caption. There's nothing extra that we are adding to our text, but this is the response that we want, and this is the image that we are attaching. All right, and we have three files here. The first is data train 90. So there are 90 training files, 10 validation files, and a total of 100 images, right? So the data train 90.jsonl file contains the training samples. The validation contains the validation samples, and these are all the images, right? So as they are saying here, to run a training job, we need to upload our data sets to a cloud storage bucket. So this is another cloud feature and another distinction between closed source and open source, right? So to use this, we need to upload our data into another cloud feature, which is cloud storage bucket, right? All right, so these are commands that are used in the Google Cloud Console, gsutil, right? So what we are actually doing here, we are actually downloading the images that we need, and we are putting them into the bucket, right? So these are just cloud commands to do all that. Okay, and so far, if anyone has to ask anything, they can ask. If you have any doubt or anything. This is pretty basic, and this overlaps into cloud technology rather than strictly fine tuning. All right, so moving on. Now these are some utility functions. The save JSON lines file, what it does, it takes a file and it takes multiple JSON objects, and then we write all those JSON objects to a file. That's all this function does. So this is just the pre-processing step. So the steps do remain same in any pipeline. We need some pre-processing. Now this is the task prompt. So why we are defining it here? Because it will remain same for every instance, which will be describe this image in detail that captures the essence of it, right? Now here, this function, this is also another pre-processing function. What this function will take, it will take a file path. So where the file is located, then what it will do, it will create tuning samples from that file. So what it actually does is that we open the file, right? And then we create a JSON object out of that file, right? So the file is an image, but we add all this, add everything else we need along with the image to send directly as a prompt to our generative model, right? So we also add the role, the parts, and the data, whatever we want, right? So this is another function that takes a file path and it outputs a JSON object, a list of JSON objects, right? And what we do is that we feed those JSON objects into this function that converts all them into a JSON lines file, which is the input to our fine-tuning job. All right. Now, again, we have a path where the training samples are stored, as there are 90 training samples stored at data underscore train 90.jsonl, where we will store our training samples, right? Then we create our instances using the function that we have defined here, create tuning samples. We give this path and it creates all the fine tuning samples that we need. And then we save them to a JSON line object using this function we defined here. All right. Now we look at one instance of fine tuning. So as you can see, we have role user and we have file data. So what file type there is. So we are using a JPEG file located at this URI images1.jpg and with accompanying text, this describe this image in detail. And we also have the model's output, right? So this time the role is model instead of user, and the model should output some text like a brown and white cat with red color and whatever caption we want the model to generate. So this is one data point for fine tuning, right? For the training set. All right, now we save this to our cloud bucket, right? And next, we do the same for our validation set. This time we have 10 samples. We also print one sample, same thing. We have some user input and what how we expect the model to generate output for it, right? And we save that also to a Google Cloud bucket. All right. So I know this can get a bit tedious at times. Okay, okay, says something. We just have to know the process, right? Not remember all this if we want to do fine tuning. So okay, so yeah, you just need to know the general steps. So if you know that I need to first of all collect data, then I need to process that data, then I need to uh, perform fine tuning, then I need to evaluate how my model perform. You just need to remember the general steps for each environment you work in, whether it be open source, closed source. The name of the functions and classes will change, how you do that will change, but the overall approach will remain the same. That's all you need to know, right? In a cloud environment, since we are in a cloud environment, use fine tuning is closed source process. There are some steps that we are doing extra, but they are useful for large corporations, right? um, like storing data to our buckets and all of that, right? In an open source environment, we have a bit more flexibility with what we want to do. We can actually use the model directly, right? So moving on. All right. So now this here, what this piece of code is doing is that we are just having a clean instance of the file and what we expect the model to generate. You know, the file URI and what the ground truth will be. And we are taking it from the instance we created earlier, right? From this, we are extracting the contents. And so this is just a bit of indexing. Get contents, then get its 0th index, which will be this JSON object. Then from that 0th index, get the parts, then get that 0th index. So it's just a bit of indexing to get the URI of this and the ground truth, right? All right, now this here will be just a clean instance of the file URI and what we want the model to generate. All right. Now we take what we have, the data table, and we convert it into a pandas data frame. Now this went from a Python list to a pandas data frame object where we have file URI and ground truth. All right. So now this is just visualization. So here is where the pillow library and IO will come to be useful, right? So it will take a bucket name and a blob name. So blob is how we store objects in cloud. So we get the storage client, and then we just retrieve the bucket, and in that bucket we get the required blob, and then we download that blob as bytes, and then we return the bytes. So this is just to fetch data from the cloud storage to however we want to use it. All right. Now we will test our model, uh, not fine tuned so far, to the base truth, right? So we define our model as Gemini 2.5 Flash, right? Now over here, this is just to display the image. So what we are doing is, so we are taking an image, naming query image URI. We are taking it from the instances, right? And what we're doing is that we get the blob and associated with that image. So wherever it is, stored in the cloud. So we get the bucket URI and we replace the bucket URI slash with nothing. So that will just fetches the blob, right? Then we read the image and then we display the image using IO library, right? And so this is our first image. Now we'll generate a caption for this image using base Gemini 2.5 Flash, and we'll see how it compares to after fine tuning. Right. Now we are using our GenAI client that we defined earlier, and we are using the models class, and then we are using the generate content function here, right? So the model will be Gemini 2.5 Flash, and the contents will be, first of all, it will be the file, and also with that file accompanying text which will be describe this image. Now this we don't need. Temperatures just tells you how creative the response should be. Zero temperature means that standard response. Zero point 0.9 means highly creative, all of that, right? But this is optional, and we'll see what it generates for us. All right. So we got the output like the image is a close-up, artful composition focusing on texture, light, and form. A person's arm clad in a flowing, voluminous sleeve of a soft peachy nude fabric dominates the left side of the frame. The fabric appears diamond. So it's pretty good, right? Because Gemini in itself, 2.5 Flash is a very huge model, right? So that is one advantage of using these closed source models. Usually they are, you know, since they are hosted on the cloud, a lot of the compute is done by the cloud. We don't need to do a lot, and so we can actually fine tune very large models, right? Like this Gemini, and these models, even the base output is pretty good, right? The caption is very good, but we will try to improve on that using the fine tuning process. Now we compare what the model generated with what we wanted. So what we wanted was this. So as you can see, this one is a bit more concise. The model's output was in 3 paragraphs. This is a single line, which a caption should be. A caption should not be, too long, right? And it summarizes what we see. All right. So now this time we prompt our model again, but this time our prompt is that we need to describe the image in detail. That's the only difference. So, here we write in detail extra. Here we just write describe this image. So they are telling us that we should see that how even just good prompting practices can get us better results, even without doing fine tuning. Okay, all right. So this generates an even bigger paragraph. Now this is even more descriptive, right? Below the sleeve, for there is a graceful hand with warm tanned skin rests gently on a rough white geometric surface. Fingers are slightly splayed, nails are neatly manicured with a natural or nude polish. The hand's position suggests a pause. So it's very good, right? Just adding these two words in our input prompt makes our output better, right? Now we can evaluate the baseline model, right, with the validation set. Now we'll go through every single prompt in the validation set, and we'll generate our output for it, and we'll generate what we wanted, right? So these are just helper functions. This get prediction will take a URI of the image and the model we want to use, and what it will essentially do is it will generate an output and it will return that output, right? And the run eval, what it will do is that it will, for each image, what we'll do is we'll get a prediction, and if we fail to get a prediction, we'll wait for 30 seconds and try again, right? And then we add the prediction to our list, and then we return our predictions. All right. Okay, now we run this. Now here is where the time library comes on, and as you can see, here we use tqdm, so we'll also see some progress bars, and these are just iter tools library. All right. Now we run our evaluation and we have a progress bar as well. Yeah, while it does that, I'll come back to the meeting and see if anyone has any doubt, and we can address that. And here you can see the difference of how a closed source model will be fine tuned as compared to an open source model. So first of all, you will require credits to access that, and then you on the Google Cloud platform, then you'll do that. I think this will take a lot of time, the way my internet is. So I think we should just go with the code first. So first, let's talk about evaluation metrics because that is important. We have not talked about this a lot. So whenever we perform a task in machine learning to evaluate how our model did, we use evaluation metrics. These are numerical representations that inform us of how our model performed. So here is a given table that tells us that for a kind of a task, what metrics are used. So if we are dealing with a classification task, a classification task is when there are multiple classes. So let's say cat and dog, and our model predicts whether an image belongs to a cat class or a dog class, right? The metrics we use to evaluate our performance are micro f1, macro f1, per class f1. So the f1 score is nothing but how many classifications we got correct, and micro f1 is the f1 over every single class. Macro f1 is the F1 for every class averaged, and per class F1 is, the F1 for one single class. It will display for all classes. If our task is summarization of text, we can use a metric like rogue L. So what rogue L does is that we have summary output that the model gives us, and we have the gold standard, what we want the model to produce. What rogue L does is that it compares both the output and the ideal output. So it will go through all the words. It will check how many words are overlapping in the form of n-grams, right? So if so let's say, what is the capital of France? The answer should be Paris, right? So if the words match, so the ideal answer will be Paris, and let's say the model also generates Paris, the Rogel will have a higher value of 1, right? But if the words don't match, and how many words match, um, Rogel will have a lower value. So 1 just means, this is the best answer we can get. This is the gold standard, right? So it varies between 0 and 100, right? Question answering, exact match, right? So if you are asking one word question, so the question I asked you, what is the capital of Paris? It needs to be an exact match. If it's not, then it's incorrect, right? Text generation, we use Blue, and we can also use Rogel. Blue is similar to Rogel, except that it focuses on precision more than recall. Rogue is more um, recall oriented, right? So for this task, since the task is image capturing, we will use Rogue, which is recall oriented understudy for gesting evaluation. So as I just explained, it just tells us how many words from the generated output and the ideal output match, right? And so it will tell us how well our is performing. So these are the evaluation metrics. All right, so just recall versus precision is given, meaning it prioritizes how much of the information in the reference summaries is captured by in the generated summary, and precision tells us which measures how much of the generated summary is relevant to the original text, right? So precision will tell us how the output that we are getting, how much of it, how much of the generated summary is relevant, right? And recall will tell us that how much of the information in the summary is actually captured. All right, and as I said, Rogue is more oriented towards precision. So that's why we were using a Rogue scorer class. Rogue one means that how many single word instances match. So if a word matches in the output and the ideal output, we will the Rogue one will increase. Rogue two means how many groups of two match. So on the, so there are two words in a row, how many two words in a row match, right? Rogue L means L stands for the longest common subsequence, so how many words at max in a common subsequence match. So in order, how many words match regardless of their position, regardless of their adjacency to each other. So I hope this clear so far. So I hope yeah, you understood what Rogue is and what other evaluation metrics are for our processes. So they, depending on what we are trying to do, we use different evaluation metrics. All right, so these are more helper functions that will just return us whatever score we got, and we just write that score down. So we'll skip over some of this because essentially, if you want to pass this lab, if you just run all the cells, it will pass. What we are concerned with is some of the machine learning code, right? Some of the fine tuning code, and we are here to study how it differs from open source fine tuning, right? And the difference that we made clear was that we are in a cloud environment, so a lot of cloud related functions, we are using buckets, we are using Vertex AI, we are using cloud AI platform to do all of the stuff for us. And now let's just skip over some of this, and let's get to how we will actually fine tune over this. All right, so we have our data sets ready. Now this is the piece of code we need to focus on, right? So what we do is, so we have the client. So if you would recall in our example of fine-tuning Quen, we used Hugging Face Transformers library to do that, which is also open source, right? Here we have a function already defined for us, which is client.tunings.tune. which creates a tuning job in Google Cloud, right? On this model using this training data set. And this is the configuration. So how we set the configuration in, PFT or R alpha and all of that. So here it does most of the work for us. We just have to specify the adapter size and the number of epochs and the name we want to give the tuned model and what validation set we will use. So what this will do is this, it will create a fine tuning job in Google Cloud that we can actually use. So this is what you need to. So you can go in depth for this code, and if you have any doubts, you can ask me. But other than that, I think so. This is just tells us when the job is running and when the job is pending. So this just so it's also written here. It will take 20 to 30 minutes. So if you know that much, we don't have that much time. So that's why you can do this at home. And if you have any doubt, you can ask me. Similarly, after fine tuning, we will again evaluate our model to test its performance as compared to the baseline model, right? We will use the same images. We will calculate the, first of all, we'll get the predictions. After that, we will evaluate using the metric rogue that we are using here, right? Rogel precision, and we'll compare both of these. And the improvement will be what we had earlier prior to fine tuning, right? Minus what we have sorry, what we have after fine tuning minus what we had before fine tuning, right? And then we normalize it using what we had prior to fine tuning, and this will give me a percentage up to 2 decimal points, right? And it will tell me how much of an improvement in numeric terms have we observed. So this is how you will concretely know that your model has you know gotten better at doing the task you wanted it to do. All right. All right. So this is just cleanup. We just delete the bucket. We delete whatever endpoint we had, and we delete the experiment. But if you want to ask anything from this cloud fine tuning example, you can ask me right now. Because this, you can go through the code in your spare time, and that will be more beneficial for you. And if you want to ask me anything, you can just ping me on Discord or WhatsApp or wherever, right? But um, that will conclude this fine tuning, cloud fine tuning for me. But if you want to ask anything, you can ask right now. Okay, says okay, so it's all right. Um, for others as well, if you want to ask, you can ask right now. Otherwise, we will move on to the last part of the slide. Okay, all right, let's just move to the last part of the slide. All right, so there's just one last thing that we need to discuss before we move on. That is what some concerns with fine tuning. So full fine tuning has high computational cost, as we have discussed earlier as well. So this is just to roundabout, conclude what we have been studying so far. So we went through everything related to fine tuning, its types, what it exactly is, what we will do. We looked through an example. We went through what the hyperparameters were, how it actually works. Now just this is just one last final thing that we need to keep in mind. What are some concerns? So of course it has high computational cost for billions of parameters. Full fine tune will update every bit. LoRa prevents this, so you don't need to be concerned with this if you are using parameter efficient fine tuning. Another concern will be risk of overfitting, right? So this is actually known as, there is a name for this, it is known as catastrophic forgetting. So catastrophic forgetting means is that when you fine tune a model, you change its behavior to match a certain behavior. But uh, when fine tuning is performed, in a not, it's not done well, catastrophic forgetting can occur. What that means is that model will behave oddly on normal tasks as well. So we don't want the fine tuning process to affect everything else. So if I want to model to talk in Shakespearean language when I ask it to, I don't want it to task in Shakespearean language when I don't ask it to, right? Catastrophic forgetting means is we forget the original weights and we only remember the fine-tuned weights for every task, for general task as well. So as it's written here, large models are very expressive. Full fine-tuning on small data sets can easily overfit. Fine-tuned model may perform worse on general language tasks, right? So for the fine-tuned task, it will perform well, but For the general task, if it's not done, if the fine tuning has not been done properly, it will perform worse on those general tasks, and this is known as catastrophic forgetting, right? Right, same thing here, right? Updating all weights that can make the model forget what it learned during pre-training. That is catastrophic forgetting. All right. Okay, all right. So we went through the code. So I did code earlier because I thought we needed to break up the monotony of the class. So we went through the code, which was closed source fine tuning Gemini, right? And now I guess we can do a few questions if there are people in the class. So, all right, let's do a few questions. So far, from what you have learned, let me ask you something. What does Q, K, and V stand for in fine tuning? If anyone can answer me, what does Q, K, and V stand for? We studied that this class. Okay, Hokesh is correct. Q stands for query, K stands for key, and V stands for value. All right, very nice. I guess we'll just do another question. The second question would be, let's see, we can ask something related to something we studied earlier. If anyone remembers what DPO stands for, what is the full form of DPO? I don't expect you to remember this because this was in first session and it was very niche. So what does DPO stand for? It is an alignment technique. That's your hint. I'll give you like 20 seconds. One, two, three, four. Okay, all right. DPO stands for direct preference optimization. So what is DPO? Preference optimization. It is an alignment technique which makes the model behave in values how we want it to. So if we wanted to not answer harmful queries, we perform alignment techniques. And one of those techniques is direct preference optimization, where we give it two examples that on a harmful query, this is what is a bad answer, this is what is a good answer. That is direct performance preference optimization. All right, so that's it for the quiz part, and now I'll take all of your doubts if you have any. All right, if you have any doubts you can ask away, otherwise we can proceed to end the session if anyone wants to ask anything. How do you decide when to do fine tuning? Okay, we also discussed this in the first class. So fine tuning has a very specific niche. So for processes where the model already has a capability to do something, but it is not the direct choice of the model to do that. So as I gave you the example, so if you want the model to write output in form of poems, a language model already had the capability to write poems, but if you asked it, it will not be able to do that. So when you want to bring out that latent behavior in your model, that's when you will use fine tuning. So if you want an image generation model to um, you know image generation model to generate images that have a specific style, that have a specific lighting, or an audio model to have certain tone, cadence, voice while generating their output. So that's when you will use fine tuning to bring out latent behavior in a model. Only use case I can see is when making a chatbot specialized on something. Okay, that is a good use case. That when you want a chatbot specialized in jargon, not exactly knowledge but jargon. Other than that, people find lots of other use cases as well, such as if you want. So that is for large corporations. For small corporations, maybe you want a model, so many companies, how they make personas with their model, right? They cannot retrain the entire model to speak as some person. So a lot of AI companies and startups are doing this nowadays, that they will have lots of AI personas that talk to them. So each persona is a fine-tuned version of the same model to use specific style. So that is also another use case, right? And all of that comes under that umbrella. Okay. All right. If anyone else wants to ask anything else, I can take that down. Otherwise, we should proceed to end the session. Okay, I think that is it. Naman, if you want to say anything, you can say. Otherwise, I think we should end. It's fine. Okay, okay. Thank you guys for attending in the final week, and thank you. Bye.